Hello everyone, this is video 12.2. We're going to be looking at moving and additivity principles about area. Yes, additivity, not an easy word to say, so if you struggle with it, that's okay. You can just say adding or addition principles about area. Um, if you've looked at 12.1, good, because we're going to need some of that for this. If you haven't yet, you might want to go back and look at it. And then again, sort of recursively, when you go back to this video 12.1, you may also want to go back and look at chapter 4 some more. So this is starting to build on a lot of things, but hopefully none of it is entirely new. So let's get started. So two principles we need to talk about, and they're both hugely important because they're going to allow us to take the area of a rectangle and change that concept and that procedure to allow us to find the area of other shapes, of other polygons, um, not just quadrilaterals. We'll use this for triangles as well later on. So the moving principle says if you move a shape rigidly without stretching it, then its area does not change. Now, there's a little bit of redundancy. This is the book's definition. And there's a redundancy there because rigidly and without stretching it are effectively the same thing. So a rigid motion is one where we're not distorting that uh, shape at all. We can flip it, we can rotate it, we can move it around however we need to, but we can't make it bigger, we can't make it smaller, we can't change any of the characteristics of it. I can't take this triangle that I'm about to move and turn it into a trapezoid of equal area or not. Rigidly means, like, imagine it's like a piece of plastic or a piece of wood, and it's not going to change. It is what it is. You can rotate, you can flip, but we're not able to stretch or shrink or anything else the shape itself. So you can see here this graphic for the area of a parallelogram. We have our parallelogram on the left, and we have our base and our height here. And we're going to talk a little bit more about this in a moment, but as a little bit of foreshadowing, this base and this height are at a right angle to each other. And it's a hugely important characteristic that bases and heights are always going to be at right angles to each other. Now, they may not always intersect, and we'll look at that here. We could do it here. I'll do it in black. So if I extend this down, so we have pretty much the shape we're going to have over on the right. I could call this the height here, out here, and then this is my base inside. And so the base and the height don't intersect, but the lines that contain them are still perpendicular. So if I take this line segment containing B and I extend it out into a line, and then the same thing with this height, I extend that out into a line. You see they still form a right angle. So this can be a little bit of a confusing point for students where they want the base and the height to always actually intersect. And so remember our variability principle. We want students to see bases and heights that intersect as well as that don't intersect. But they do always have to be at a right angle. Anyway, so the point was that I'm going to take this triangle here, and I'm going to move it into here. And now when I do that, I get this shape over on the right. Now, this is a rectangle, and there's a little bit of understanding that we have to do to be able to convince ourselves, uh, ideally to prove, that this is a rectangle. Number one, we know that the base and the height are at right angles to each other. We already mentioned that. And so we know all these angles are right angles. So that's part of being a rectangle. That's not very convincing. And then we need to know that the opposite sides are parallel or congruent. Now, the fact that these are all right angles is actually going to make them all parallel already, but just to be complete or thorough or even borderline redundant, we know this is the height, we know this is the height, so we know that these two sides, H and H, they're both heights. And then because it's a parallelogram, we know that these two sides were congruent before, and we've cut this base and we've moved it over here. And so this piece we've moved over here. Well, it hasn't changed. And this is the importance of this rigidity part. When I move that piece over, this length over here was B. This length over here is B. It's not the same segment because we've switched the pieces around, but it is the same length. If we were to take this rigidity qualification out of it, I could take that line segment off, stretch it, shrink it, put it back, and now this base wouldn't be the same length. So the rigidity is a huge piece to this because it makes sure that we preserve the lengths and areas of these objects. So we can cut this little triangle off, we move it over here, we get this rectangle. The area of this rectangle is base times height. That's what we talked about the area of a rectangle to be. We may think about this as length times width, but it's the same idea. It's still these two dimensions, these two perpendicular dimensions being multiplied. So this is my area of my rectangle. So how do I know this is the same as the area of this parallelogram? Well, because I've just taken this piece and moved it over. It's the same area, it's the same amount of region, it's just been rearranged. And so we have not created or destroyed any area. Again, that's a hugely important part of this rigidity qualification. If I were to take that triangle off, stretch it, shrink it, and put it on, then I've either created or destroyed area. So by making sure that everything stays the same, that's not the case. I may be over explaining this. That's okay. But this is a hugely important point because it allows us to take shapes and make them into other shapes. And so now area formulas or areas that we don't know how to find, we can turn those shapes into areas where the areas we do know how to find, and then this is how we develop and build our area formulae. The other important principle is this additivity principle. And the additivity principle says if you combine, and this is again from the book, a finite number of shapes without overlapping them. Now, there's also a part that all the pieces together have to form the original shape. So not only can they not overlap, they can't leave any gaps either. So there's like a little bit of an idea that's missing here, that everything has to be included. This is what we call mathematically, what the mathematical term for this would be a partition. And so, I mean, if you think about like where you've heard that term possibly before, like if you put a wall through a room, when you put that wall in there, you haven't lost any floor space, unless you create like a top secret panic room or something. But even still, the panic room still has floor area to it. It's still there. But when you put a wall through there, you've taken one room, you've turned it into two rooms. You haven't made anything any bigger or smaller as total area. You've just created more rooms. And so this is the same thing we're doing here. This T shape looks kind of irregular. So by putting this wall through here, we break this into two rooms that are both rectangles. So this T as it is would be kind of hard to find the area of, but by putting this line through here and breaking it into two rectangles, we can find the area of these two rectangles. So this is 12 by 6 here, so that's 72. This is 10 by 5 here, that's 50. And we add that all together, and the sum would be 122 square centimeters. It's not 72, it's not 50, it's 72 plus the 50. Now, this is not the only way to break this T up. And so you could also put the wall through here and put a wall through here. And so in doing so, we would have 3 rooms. This is a little bit harder to do though because we don't necessarily know all the dimensions. We would know that this large rectangle in here, it's 5 by 16 because this is 6 and this is 10. So this would be 5 by 16. We wouldn't know these individual areas though, but I will let you think about as sort of an extension, as sort of a bonus checkpoint problem. We can't find these two areas individually, but we can find the sum of those two areas. So I'll leave that problem for you to think about how we could do that. There's not really a huge reason for us to do it this way, it's breaking it into 3 regions instead of 2 regions, and typically we want the smaller number of moving parts. It's easier to make mistakes with 3 things than 2 things because you have an extra thing to work with. And it's also a little more difficult because we don't know these individual links, so that makes it a little bit harder of a problem. So I wouldn't do it this way, but the point is I could. It is possible still to do it this way. You can see here a better example of what I was talking about on the previous slide. I could put this wall through here, or draw this line through here, and now I see that I've got 10 by 2, and that gives me my 20 here. And then here I've got my 6 by 4, and that gives me 24 there, which gives me 44. So this is the way we split up that T on the previous slide. That circles kind of bother me. All right. Or we could draw our lines here and break the T up this way. It looks like a T-shirt now. And so we've got 6 by 6. Now, this 6 is obvious because it's down here, but this other 6 may not necessarily be so. So working with students for them to understand that this is a square, so all of these are 2's, all of these are 2's. And so now this is 4 from here to here. This is 2 from here to here. And so this whole thing is also going to be a 6. So this is a square, a 6 by 6 square. This is 2 by 2, which is a 4. This is 2 by 2, which is 4. And so again, we get 44. This idea that I could take a shape and break it up multiple ways and still get the same area is fairly counterintuitive for some students. So be prepared to work with students on figuring out what these various lengths are. A lot of students are going to want this rectangle here to be 6 by 4 because they're going to look at this 4 and look at this 6 and want this to be a 24. So you're going to maybe work with some students, maybe you're going to have to work with some students to understand that this amount is 4, this amount is 2, so this whole amount is 6. All right. The other way the additivity property works is not really by addition, but really by subtraction, or you could think of as adding a negative region. And you'll see that written in some places, and you'll hear people say that sometimes. They'll talk about this as negative area. And so I want to find the area of this shaded region. The larger rectangle is 40 centimeters squared. We can see the 8 and the 5. It doesn't make an awful lot of sense in this case to break this up into smaller rectangles. It's going to be a little bit harder to do. We may not have all of the shapes in order to add up these 4 rectangles. So doing it by addition, not going to be the easiest approach. So the better way of doing this is by doing it by subtraction, by adding in this negative area. So I want to remove this rectangle, which is 12 centimeters squared. And so I've got the big rectangle. This whole shape is 40 centimeters. I want to cut out this rectangle, which is 12 centimeters squared, and then that leaves me with 28 centimeters squared as my area. You can probably see where this can go wrong with some students. I mean, you've got to be able to find the area of the large rectangle. You've got to be able to find the area of the small rectangle. You've got to be able to do the subtraction correctly, and you got to be able to keep the units correct. So again, a lot going on in this problem. Really easy for students to make mistakes on this one. Going through a lot of examples, helping students understand when to add and when to subtract. What are the cases where it's better to do one or the other? So for your checkpoint problem, here's this shape that looks vaguely like a western state. So I want you to find the area of this, but by doing it by addition and by doing it by subtraction. So look at this problem in both ways. Think about both approaches, and hopefully that'll help tune your eye to solving this by addition as well as by subtraction. If you have any questions about this problem or any other problem from the video or from the section from the book, as always, please bring them to class and we'll get them answered. All right, thanks.